Shereshkian and Wax defined a Q analog of the chromatic symmetric function. Their definition makes it a quasi-symmetric function in general, although the special case that we care about is actually a symmetric function. I suppose for selfish reasons I could just go right to the symmetric function special case, but since everybody talks about this function and calls it a quasi-symmetric function, I want you to know what it is in general so you'll understand where that name comes from. First of all, let me introduce some notation. Given a composition alpha of n, I'm going to write alpha, sort of the same symbol that we use for a partition, except I'm going to make a double horizontal bar. So that means that alpha is a composition of n. Now we call a function in any number of variables, x1, x2, etc. Quasi-symmetric if for all compositions alpha, let's say alpha 1 through alpha r of n, the coefficient of x1 to the alpha 1, x2 to the alpha 2, etc., xr to the alpha r equals the coefficient of xi1 to the alpha 1, xi2 to the alpha 2, etc. whenever I1, I2 up to IR is a strictly increasing sequence. So for example, if we have x1 squared x2 plus x1 squared x3 plus x2 squared x3 plus x1 squared x4, etc., plus 3 x1 x2 squared plus 3 x1 x3 squared plus 3 x2 x3 squared plus 3 x1 x4 squared, etc. That is quasi-symmetric. This is not symmetric because the coefficients of x1 squared x2 and x1 x2 squared are not the same. Now this function is usually written capital M 2 1 plus 3 capital M 1 2, where capital M alpha equals the sum over all sequences of increasing indices xi1 to the alpha 1 dot 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 xir to the alpha r. This is called the monomial quasi-symmetric function. Let's let q-sim sub n be the z module of quasi-symmetric functions in variables x1, x2, etc. in general in infinitely many variables, so with integer coefficients. The most natural basis of q-sim n is the basis of all monomial quasi-symmetric functions where we let alpha vary over all compositions of n. One thing to note is that every symmetric function is also a quasi-symmetric function. For example, the monomial symmetric function m lambda is a sum of quasi-symmetric functions m alpha, where the sum is over all alpha, which are rearrangements of lambda. So m21, little m21 is big M21 plus big M12. All right, let's look at chromatic symmetric functions and see how they're related to quasi-symmetric functions in the first place before we look at a Q analog. So for a graph G equals VE, which is undirected simple graph, we define xg, the chromatic symmetric function, of G to be a sum over lambda, the number of proper colorings of G of type lambda times m lambda. And a proper coloring of type lambda means that adjacent vertices must have different colors. That's what proper means. And type lambda means that we have lambda 1 vertices of color 1, lambda 2 vertices of color 2, etc. Now observe that since color numbers are arbitrary. So we could call blue color 1 and red color 2, or red color 1 and blue color 2. We have that the number of proper colorings of G of type alpha equals the number of proper colorings of G of type lambda if alpha is a rearrangement of lambda. So if we extended the definition of chromatic symmetric function to count proper colorings of type which is a composition rather than a partition, we wouldn't be getting anything new. We'd get all the same colorings. Alright, so now let's look at the Q extension. So for each coloring, let's say kappa, we can look at this as a function from the vertices to the positive integers. Define the number of G inversions of K to be the number of pairs ij in the edge set with I less than j and the color of K less than the color of I. Now let's define xgq to be the q-chromatic quasi-symmetric function of G to be, we won't put just the number of colorings, we're going to put Q to the number of inversions in a coloring next to a quasi-symmetric function capital M alpha. So this will be a sum over all compositions alpha of n, a sum over all colorings, proper colorings of type alpha, Q the number of inversions of K. We'll put that sum next to the quasi-symmetric function capital M alpha. Now unlike the Q equals 1 case, now when Q equals 1 here we're just counting colorings. So we have the chromatic symmetric function SG. Unlike in the Q equals 1 case, this does not end up being symmetric necessarily. Let's do an example and see why. let's look at the graph that has 3 vertices, 1, 2, and 3, with 1 connected to 2 and 3, 2 and 3 not connected to each other, well, not adjacent. And let's make a table of coloring types and colors of vertices 1, 2, and 3. And then q to the number of inversions of the coloring. So if we look at, so there's no colorings of type 3, because that would mean we'd had 3 vertices that are not adjacent to each other. We don't have that. But we could do a coloring of type 2, 1 by giving vertices 2 and 3 the first color and vertex 1 the second color. And that's the only way we could do it, because these are the only pairs of vertices that could possibly have the same color. So similarly, we could have a coloring of type 1, 2, where 2 and 3 got color 2, and the one vertex 1 gets color 1. And then, of course, there's colorings of type 1, 1, 1, where we give the vertices colors 1, 2, and 3, 1, 3, and 2, etc. All possible 6 permutations of that. These are never going to have inversions, because an inversion requires I'm sorry, these are going to have inversions. In fact, maybe we should write out all of them. So 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. All of type 1, 1, 1. Alright, now let's look at vertices that have a smaller label but a greater color. And they have to be connected by an edge. So in the first coloring, we have 1 is less than 2 and 1 is less than 3, and it got a bigger color each time. So that contributes q squared, 2 inversions. Here, 1 is connected to 2 and 1 is connected to 3 by edges. But 1 got a smaller color, so that's fine. So that's q to the 0th, or 1. Now, here 1 gets a smaller color than 2, gets a smaller color than 3, so there's no problem there. Here, 2 gets a greater color than 3, but they're not connected by an edge, so that's okay. Here, 1 gets a greater color than 2, and they are adjacent, so we get 1 inversion. Here, 1 gets a greater color than 3, 2 gets a greater color than 3. But 2 getting a greater color than 3 doesn't matter because there's no edge, so we still have just 1 inversion. 1 gets a greater color than 2, 1 gets a greater color than 3. So that's 2 inversions. And then here, 1 gets a greater color than 2, 1 gets a greater color than 3, 2 gets a greater color than 3, but we don't care because they're not connected by an edge, so that's q squared. So here xgq equals q squared m21 plus 1 m12 plus, for colorings of type 111, we have 2 plus 2q plus 2q squared m111. You can see this is not symmetric because capital M21 and capital M12 did not get the same color. But the q equals 1 specialization is 1m21 plus 1m12. So that's m21 plus 6m111. So that is symmetric. Now also changing the labels of the vertices of a graph can change the q-chromatic quasi-symmetric function. So changing the vertex labels changes this function. So let's change the labels and do this again. Let's switch 2 and 1. And record the coloring type and color of the vertices and the contribution to the symmetric function, the quasi-symmetric function. Alright, so we should have the same numbers of colorings because vertex labels are arbitrary. So we have one coloring of type 2-1. That's if 1 and 3 get the same color, color 1, and vertex 2 gets color 2. And now if we're going to have one vertex of color 1 and 2 of color 2, the 2 of color 2 have to be 1 and 3. And then we can color the vertices 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Well, let's see what the q to the number of inversions is going to be. So here we have 2 has a greater color than 3, and there's an edge between them, so that's a 1 inversion. Here, let's see, 1 has a greater color than 2, and there is an edge between them, so that's q. Here, 3, so vertex 2 has a greater color than vertex 3, that counts as q. Vertex 1 has a greater color than vertex 2, and they've got an edge, so that counts as q. Vertex 1 has a greater color than vertex 3, but that doesn't matter. Vertex 2 has a greater color than vertex 3, and that does matter. Three, 1, 2. Vertex 1 has a greater color than vertex 2, and a greater color than vertex 3, but that doesn't matter. Just the vertex 1 and 2 matters. And now vertex 1 has a greater color than vertex 2 and 3, but that doesn't matter. Vertex 2 has a greater color than vertex 3, so that's 2 inversions. So now this chromatic quasi-symmetric function looks like we have q m21 plus q m12 plus 1 plus 4q plus q squared m111. Now these two monomial quasi-symmetric functions have the same coefficient, so this is q times m21, little m21, plus 1 plus 4q plus q squared, little m111, which is the same as big M111. So again, we have the same q equals 1 specialization, 1, 1, and 6, 1, 1, and 6. But this is symmetric even before we specialize. Now, Qureshi and Wax figured out a sufficient condition for the quasi-symmetric function to be symmetric. If P is a unit interval order, with an altitude respecting labeling, then the quasi-chromatic quasi-symmetric function is symmetric. Now recall what altitude respecting labeling means. So altitude of an element, say x, is, well, let me say I. Altitude of an element I is the number of elements in the poset less than I, sorry, greater than I, minus the number less than I. No, I did it right the first time. Less than I minus the number greater than I. And altitude respecting means if the altitude of x is less than altitude of y, then x must get a lower label. I actually took both of these graphs to be incomparability graphs of posets. So the incomparability graph of 2 less than 3 and 1 incomparable is the first graph. And the incomparability graph of 1 less than 3 and 2 incomparable is the second one. So what's the difference between these two posets? So this bottom element without naming the elements. So if we count number of things below minus number above, that gets -1. Here number below minus above is 0. And here number below minus number above is 1. So that means that this should get the least label, that should get the second least label, and this should get the highest label. So the second poset follows that rule. It has an altitude respecting labeling. And that's what makes this graph have a chromatic quasi-symmetric function that's symmetric. This poset does not follow that rule, because the element of altitude 0 got a lower label than the element of altitude -1, which is what makes this graph have a chromatic quasi-symmetric function which is not symmetric. Alright, now since the chromatic symmetric function, the q-chromatic symmetric function in this case, is symmetric, we know that the coefficients in the different basis expansions have to be evaluations of Hecke algebra characters at certain elements of the Hecke algebra. And those certain elements are Quasi-Symmetric basis elements. So let's say we have W in the symmetric group avoiding 3, 1, 2. And let's let P be the path poset of the descending star network FW. Let's let this be the corresponding unit interval order. Then the q-chromatic quasi-symmetric function corresponding, well, which is symmetric, the q-chromatic symmetric function corresponding to the incomparability graph of P equals the trace generating function of the Quasi-Symmetric basis element indexed by W. That is the sum where we put the induced sign character evaluation next to the monomial symmetric function m lambda. So to see this, first of all, the path poset of FW inherits an altitude respecting labeling always. Now let's let G be the incomparability graph of P. So let it have vertices V and edges E. Now if we're given a coloring kappa of G of type lambda, a proper coloring, let's create a tableau U by putting elements of color I in column I. Actually, let me use a different letter. Let's put elements of color, let's say C, in column C, so that I can use I for something else. Now let's observe that elements I and J form a G inversion if and only if, first of all, I is less than J, and then the color, which I can write as kappa, kappa of J is less than kappa of I. and I and j as a pair belong to the edge set. Now these conditions, if we think in terms of the post set, well, I is less than j as integers is the same thing. Color of j less than color of I, well, we put elements of color C in column C. So that means that j appears in an earlier column than I. And then ij is an edge. Now the incomparability graph has edges which are defined to be pairs of elements that are incomparable in the post set. So that means that I is incomparable to j in P. Now these conditions are precisely what it takes for I and j to form a P inversion in the tableau U. So that means that the sum of colorings q to the number of G inversions in the coloring equals the sum over tableau q to the number of P inversions in the tableau. And if we're putting all the elements of color C in column C, we might as well put them in increasing order. So that means that our tableau is going to be column strict. So that gives us that the coefficient of m lambda is exactly what we know the induced sign character evaluated at CW to be. So that means that the q-chromatic symmetric function of the incomparability graph of P equals, so in addition to a sum of, I'll write this again, in addition to that sum, which is yq of the Cauchy-analytic basis element, it's also a sum of irreducible character evaluations next to Schur functions. And it's also a sum of monomial trace evaluations next to elementary symmetric functions. And we could do all the bases. The end.